Hello, everyone. Today we will introduce Bubble Sort. The key idea is to swap out of order adjacent elements. In this video, we will concentrate on ascending order, that is, elements are arranged from small to big. The smallest element is put in the first position, aka the leftmost position, while the biggest one is put in the last position, aka the rightmost position. You can easily work on descending sort after you learn the idea. Treat elements as bubbles. Let bigger bubbles sink to the right end. Suppose we have an array with elements 3, 4, 1, 5, and 2. After ascending sort, the array is rearranged as 1, 2, 3, 4, and 5, shown in the bottom diagram. In this slide, we introduce adjacent elements. Two elements next to each other are adjacent. In the above lineup, elements 3 and 4 are adjacent. So are 4 and 1. However, 3 and 1 are not close to each other, so they are not adjacent. We then introduce the order of adjacent elements. Two adjacent elements are in order if the left element is smaller than or equal to the right element. Otherwise, we would call these two adjacent elements out of order. For example, 3 and 4 are in order adjacent elements, while 4 and 1 are out of order adjacent elements. What is the key of bubble sort? Let us examine an array where each adjacent pair is in order. In that case, the array is sorted already, we do not need to do anything. The above observation raises a question: what to do with out of order adjacent pairs? Let us concentrate on one step at a time, how to put the biggest element to its proper place. That is, how to sink the biggest bubble to the rightmost position. The rule to put the biggest element to its proper position is simple. Starting from the beginning of the array, examine all adjacent pairs, swap them if they are out of order. For example, elements 3 and 4 are adjacent. Since they are in order, do nothing. Observe that we have examined two elements, 3 and 4, in the array so far, and 4 is the bigger one and it resides on the second position after being processed. Note that the remaining 3 elements are not processed. We put them in a dashed line box. Afterwards, we move to the next adjacent pair. Adjacent elements 4 and 1 are out of order. Swap them. After swapping, 4 is the biggest of 3 elements and it resides in the third position. Then we continue to the next adjacent pair. Adjacent elements 4 and 5 are in order. Do nothing. Note that 5 is the biggest of the first 4 elements that are examined, and it now resides in the fourth position. Adjacent elements 5 and 2 are out of order. Swap them. Element 5 is the biggest of the first 5 elements, and it now sits on the fifth position. Since all adjacent pairs are examined, we are done. Now element 5 is put in proper position. Put a smiley face on it. In this slide, we will outline a pseudocode to put the largest element to its proper position. Suppose we have an array R with an element. The first index is always 0 and the last index is n minus 1. For example, given an array of 5 elements, the first index is 0 and the last index is 4, which equals 5 minus 1. To represent an adjacent pair, we are going to use indices. For an adjacent pair, if the index of its left element is I, then the index of its right element is I plus 1. Hence, we will use variable I to represent left index of any adjacent pair. The left index of the first adjacent pair is 0, while the left index of the last adjacent pair is n minus 2. For example, when n is 5, the left index of the last adjacent pair is 3. Thus, the range of left indices of adjacent pairs is 0, n minus 1, where 0 is included and n minus 1 is not included. Here comes the code. Let variable I represent left index of an adjacent pair. It starts from 0, as long as I is smaller than n minus 1, we do the following. If the element at index I is larger than the element at index I plus 1, that is, this is an out-of-order adjacent pair, swap them. Afterwards, move to the next adjacent pair by increasing I by 1. If we run the above code on the left diagram, we will get the right diagram. That is, put the biggest element to its proper position after sort. Let us summarize what we have learned so far. By swapping out of order adjacent pairs, we put the biggest element to the rightmost position. So far so good. Now comes the $64 question. How to sort the array. We would like to set every element to its proper position, not just the biggest one. This is what we plan to do. We will put the first and -1 biggest elements to their proper positions, then the remaining one, that is, the smallest element, must be in its position. For example, by some approach we will discuss soon, we put the second biggest element 4 to its proper position. After the first two biggest elements are put in proper positions, we put the third to biggest element 3 to its proper position. Keep on going until we put the n-1 biggest element, that is, the second smallest element, 2 in this example, to its position. Now, the smallest element has no other place to go other than the first position in the array. So, how can we put the second biggest element to its proper position? It is easy. Since the biggest element is its proper position already, we just focus on the subarray that consists of the first and -1 elements. By swapping out of order adjacent elements in that subarray, we put the second biggest element in proper position. The code is shown as follows. It is very similar to the code to put the biggest element to proper position. The only difference is the immediate unreachable upper boundary of the left indices of adjacent pairs is changed from n-1 to n-2, since we check one fewer pair of adjacent elements. After we run the code in slide 10, then this segment, two biggest elements are put in proper positions. See the smiley faces on 4 and 5? That means both elements are in proper positions already. Here is a complete code of bubble sort. Look at this table. To put the biggest element in position, we examine all adjacent pairs whose left indices ranges from 0 to n-1, where left close bracket means 0 is included and right open parenthesis means n-1 is not included. To put the second biggest element in position, we examine one few adjacent pair. So the left indices ranges from 0 to n-2. Keep on working. Now we come to the task to put the n-1 biggest element to position. The only adjacent pair we need to work is the first, where left index is 0. Now let us explain the code. Variable j represents the immediate unreachable upper bounds of left indices of adjacent pairs. It starts from n-1, decrease 1 in each round of outer loop, until j moves down to 1. In the inner loop, we swap out of order adjacent pairs whose left indices ranges from 0 to j, where 0 is included and j is not included. In this slide, we provide a code of bubble sort using C++. To swap out of order adjacent pairs, we do the following. First, put ARR at I to variable temp. Secondly, put ARR at I plus 1 to ARR at I. Thirdly, put temp, which holds the original value of ARR at I, to ARR at I plus 1. You can draw lines to see how the steps work. In the last slide, we will discuss complexity of bubble sort. To put the biggest element to position, it takes n-1 comparisons. To put the second biggest element to position, it takes n-2 comparisons, and so on. To put the n-1 biggest element to position, it takes one comparison. It remains to find out the sum of n-1, n-2, all the way to 1, which is n-1 multiplied by n, then divided the product by 2. The complexity of bubble sort is O(n) square. Conclusion: bubble sort is simple. It works well for arrays with small sizes, but unsuitable for large size. For an array with many elements, quicksort is a better option. Thank you for watching.